Another way of characterizing dynamic systems is there using the inverse Laplace transform of this function, which is the impulse response. Now, impulses are not very practical. It means a lot of energy in a very short time. So for measurement equipment, that's not very practical. We usually take the integral and take the step response. So measurement of the dynamic behavior is usually done with this step response because it's far more practical. And then we have a step response, for example, like this. And we talk about delay, rise time, which goes from 10% to 90%, overshoot, and all kind of characteristics of such a curve. But of course, the reality can be much more complex than just a few numbers as displayed here. This is a real plot from a oscilloscope. Important to know is that there is a relation between the impulse response and, of course, this whole differential equations and the poles and the zeros. And this is given by the inverse Laplace transform. And I don't want you to know this formula exactly. The most important thing of this formula is that you say that the impulse response is a sum of exponential phenomena in which the pole is the argument, p times t. It means that if p has a positive real part, this explodes for t goes to infinity. And this means that if there is a bounded input signal, but the poles are such that we have a positive real part, that the output will go to infinity. And we call that unstable. So from this expression, the only thing you need to remember is that the poles must have a negative real value for a system to be stable. And that is what is written here.